Hello for everyone who's watching this video. I'm Keunwoo from KAIST HCI Lab. Sadly, due to the coronavirus pandemic, KAI 2020 physical event couldn't be held. So I'm recording this video to explain my work MagTouch, which has been published in this year's KAI. MagTouch is a robust finger identification method for a smartwatch that uses only a smartwatch and a magnet ring. This is a collaborative work done by KAIST and the University of Virginia. Smartwatches are becoming more and more popular these days, and they are also getting more powerful. However, its size is still small. But it should be small because it's a watch, right? But the problem is that its small touchscreen size limits the input space of the smartwatches. Several solutions have been proposed to cope with this problem. For example, it attaches wearable sensors to fingers. It uses raw capacitive data from the touchscreens and uses computer vision technologies. However, wearing sensors for interaction might interrupt our daily activities. Furthermore, the methods that used capacitive images required users to pose exaggerated postures, or multiple fingers should be contacted on the touchscreen. In case of computer vision technologies, a camera should be attached far from the interaction area due to its field of view, and it led to larger hardware sizes. As a solution, we represent MagTouch. MagTouch's hardware configuration is simple. It only needs an off-the-shelf smartwatch that has a 9-axis IMU sensor and a magnet attached to a ring. Magnets have been used in various HCI projects because it is an active signal source, even though it doesn't require power. We chose a ring form factor. The ring is a common type of accessories, and we thought it is less interruptive. MagTouch can classify index, middle, and ring fingers. Now, I'll explain how MagTouch works. If we know the location of the center of the hand and a touch point, then it is possible to classify fingers. For example, if the touch point is on the left side of the hand, then the tap must be done by an index finger. If it is on the right side, then it is a ring finger, and middle finger for the center area. So the question is how to get the location data of touch point and the center of the hand. The touch location is easy. We can get from a touch point. For the hand center location, the magnet ring provides it. It doesn't mean that we have to track the 3D location of the magnet. Actually, it is not possible to track 3D location of a magnet only using a single magnetometer inside the smartwatch. In fact, we need to know whether the touch point is on the left side or the right side of the hand. It is much easier than tracking, but still, it is quite complex to create an accurate model. Therefore, we use machine learning. The input of the machine learning model is a touch point and the magnetic field of the magnet ring measured by the smartwatch. We used SVM as our machine learning model. However, there are two challenges. The first one is about the ambient magnetic field, and the second one is about the relative posture of the two arms of the user. I'll explain about the challenges with images. Let's start with the ambient magnetic field problem. The principle that I explained earlier is valid only when there's no other magnetic field except the magnetic field from the ring. However, there are ambient magnetic fields in the typical environment, mainly from the geomagnetic field, and it is fixed to the Earth coordinate. The ambient magnetic field measured from the smartwatch changes based on the user's direction on the Earth. In other words, it is the direction that the user is facing. Therefore, based on the user's direction, the measured magnetic field is not always the same, even though she touches the same point with the same finger. Second, the arm posture problem. A user can tap the same point from different angles, as this picture shows. Then, the measured magnetic field is not the same, even though the used finger and the touch point are the same. In other words, the posture of the two arms can affect the total measured magnetic field. We suggest two solutions for the two problems. MagTouch eliminates the ambient magnetic field with only a single magnetometer. It is done by a module called CAME. CAME stands for Computational Ambient Magnetic Field Eliminator. Moreover, MagTouch handles various arm angles by collecting data from various arm postures. This is the overall pipeline of MagTouch. First, it estimates the ambient magnetic field with the CAME module and subtracts it from the measured magnetic field to get the ring's magnetic field. The magnetic field and the touchpoint data are combined and fed into the machine learning model. The machine learning model is trained with various data to handle different arm postures. So let's talk about the CAME module in more detail. How does CAME estimate the ambient magnetic field? CAME saves the ambient magnetic field when the magnet ring is not near the smartwatch. When the magnet ring approaches, then MagTouch detects the magnetic field distortion. And it subtracts the saved ambient magnetic field from the newly measured magnetic field. As a result, we can get only magnetic field from the magnet ring. However, just simply saving and subtracting the ambient magnetic field is not enough, because a user can rotate while using MagTouch. For example, a user might walk around the corner or spin around. Here's why the rotation of a user can be problematic. The ambient magnetic field should be fixed on the earth coordinate. However, if we save the raw magnetometer data, which is in the sensor frame, then the ambient magnetic field rotates with the smartwatch, which is incorrect. Therefore, if the smartwatch rotates, MagTouch rotates the saved ambient magnetic field to the opposite direction of the device rotation to continually keep its direction in the earth frame. This process is converting the saved ambient magnetic field from the sensor frame to the earth frame for every new sample. This is possible by estimating the orientation of the smartwatch using an IMU sensor. Next, we did a user test to evaluate MagTouch for different people and different situations. It was divided into 2 days. On the first day, we collected training data for a machine learning model. On the next day, we did real-time tests for different directions and different contexts. Each participant provided training data in 4 different postures, as this picture shows. These postures include various possible arm angles with some extreme cases. Random targets appeared on the smartwatch, and the participants had to tap the targets with the corresponding fingers. In total, 816 samples were collected for each participant. We trained a personalized machine learning model with this data. Participants faced the same direction during the training sessions. The test was very the same as the training. The participants tapped randomly appeared targets with corresponding fingers. Furthermore, MagTouch classified the fingers for every tap in real time. However, we wanted to know whether MagTouch is robust to ambient magnetic field change. Therefore, we asked the participants to face 4 different directions while tapping the targets. In addition, we asked the participants even to rotate while using MagTouch to change the ambient magnetic field continuously. As a result, we tested 510 tap samples for the directional testing for each participant. The second test followed right after the first test. This test was to capture various arm postures that can happen during everyday activities. Each participant did the main task, and intermittently the smartwatch vibrated and they tapped 10 to 12 random targets. The main tasks were reading and typing, which represents the releasing situation and working situation. This is the result. MagTouch showed 95% of an accuracy. The red bars are MagTouch's accuracy. The green bars are accuracies that calculated by using raw magnetometer data, which has the ambient magnetic field problem. The results show that MagTouch could classify fingers in different directions and in rotating situations. Furthermore, it could handle posture variations in reading and typing situations. In comparison, raw magnetometer data showed poor accuracies when the participants faced different directions and different usage contexts. It shows that MagTouch could solve the two major problems, which are ambient magnetic field and arm posture problems. MagTouch can be used in various applications. For example, a mail application can have a single large button for multiple functions rather than having small 3 buttons. This makes it easier for a user to access different functions. In this context step scenario, a user can directly access different functions for each item. This would not be possible in current UI because the item size is too small. As a conclusion, MagTouch is a robust and practical finger identification method which only requires a smartwatch and a magnet ring. MagTouch handles the ambient magnetic field and arm posture problem with computational magnetic field elimination and machine learning. I want to thank my great colleagues Daehwa Kim, Seongkook, and my advisor Geehyuk. This is the end of my talk, and I wish I could get questions directly from the audiences, but unfortunately I can't. So if you have any questions, please visit my homepage. You can get more information about this research, and please feel free to send me some questions if you have. Thank you.